Good morning, everyone. I'm really pleased to be able to join you this morning. My name is Rachel Klima. I am a staff scientist in the Planetary Exploration Group over in the space sector. And my background as an undergrad is actually in pure geology, but I considered double majoring in geology and astronomy. And I didn't even know that there was such a field as planetary geology when I started out. So I think this talk is a little bit of an ode to the Apollo era that created the field of planetary geology. I'll tell you a little bit about that. So what I'm going to do, I'm going to introduce some of the science of the moon, but really what this is all revolving around is why we're going back to the moon, why NASA and the planetary scientific community, and even beyond that, why we have an interest in not just landing on the moon, not just another boots on the moon activity, but how creating a sustained presence and how that will help the nation and really humanity. All right. So why do we want to return to the moon? There's very often I get this question. I think about this question because I would like to really convey to people that are not necessarily science fiction enthusiasts or science enthusiasts or folks that just naturally really have a drive for exploration. What is the point in investing money in returning to the moon, especially investing in a place that we've been there, done that. So there's a lot of science that is left to be done on the moon. I'll talk for several slides after this about that in a bit more detail, but the moon and landing on the moon and returning samples is what really opened up our understanding of the evolution of Earth, the evolution of other planets in the solar system, and even planets beyond our solar system. Beyond that, it tells us a lot about the flux of things like impactors into the Earth-Moon system. So we'll talk about it in more detail. One of the things that I think resonates deeply with folks as far as why humans need to do planetary exploration rather than, we had the Apollo era and human exploration of the moon, human landings on the moon. But since then, we've had a vast array of robotic explorers to the moon, to Mars, throughout the solar system. So one of the questions is, why do we need humans to do this? Can't we just do it with robots? And while that is true to some extent, there are decisions that the human mind makes. And beyond that, there's even just this ability when a human being with human eyes experiences these things, for them to convey that excitement and to convey their experience to others in a way that you just cannot do in the same way with a rover on Mars and whatnot. And I think one of the ways that we really see this and try to evoke the same kind of feeling is with a lot of these things like Twitter feeds. For instance, in the case of Messenger, we had a tweet that went out about that was in the first person, as if the spacecraft anthropomorphized the spacecraft to talk about its final impact, and it was probably the most well received and emotional tweet that we had out of the Messenger program. And similarly, there have been things for those who are interested in space exploration that followed the Rosetta mission. When Philae left Rosetta and landed on the comet, there was just so much more engagement by the public with these beautiful cartoons that ESA put together of the little spacecraft going off. But when you have actual humans there and you have humans that are able to view something, talk about the beauty of Earth, the humbling experience of this, it's something really, really special. So all of that, warm fuzzies aside, developing technology, learning to live off-world are incredibly important for the sustainability of the human species. So, to understand what the limitations are, the moon is really a fantastic place for us to be able to do that. And then finally, especially at APL, something that we need to consider as a support of the government and the nation is that demonstrating the commitment to the peaceful exploration of space and being leaders in how we explore and setting the international standards for how we explore and how we behave as humanity in space is incredibly important, because we've reached a point where people are going to go, whether it's rich people, whether it's other countries, people are going back to the moon. And so NASA, APL, the United States, we need to show a commitment to be there and to help set the behavioral standards that we would like everyone to be following as we move into space and become a multi-planet species. All right. So as I mentioned at the beginning, the moon is really the cornerstone of planetary science and solar system exploration. This is an example of one of the samples brought back from the Apollo mission and a beautiful picture of the lunar surface. Having these samples, so especially as a geologist, having a physical sample that we know where it was picked up from on the moon is incredibly critical for understanding the geology of how the moon formed, and in turn, understanding how planets throughout the solar system form. And I'm just going to show you here. Let me click it again. So here's a picture of the moon. The first picture was, a standard image looking in visible light. This is an image that was composed by images taken with an imaging spectrometer flown on the Indian mission Chandrayaan-1, but it was a US instrument. And this type of image displays what the actual composition of the rocks are. So basically, by having samples back from the Apollo mission, by studying them in the lab on Earth, we were able to understand how the light interacts with the surface and to exploit the light reflected off the surface of the moon to map out what the rocks are all across the moon, not just in the places where we landed. And this synergy between the robotic spacecraft and the samples returned by humans really formed the core of how we can take these techniques that we learned and employ them on other bodies in the solar system. So one of the things that we learned through studying these samples is that planets of the size of the moon and beyond basically evolve as magma oceans. So you have this extremely hot ball of molten rock that forms, and depending on the size of the body, you have all kinds of different things following crystallization sequences, and you form the crust of the planets. And you can understand through studying the differences in the rocks on the moon, the meteorites that we have from Mars, and the rocks on Earth, why things like plate tectonics kicked off on Earth, but not on the moon. You have substantial amounts of water, you're able to generate a dynamic crust and really lead to something like we have on Earth that enables life across the planet. In addition to understanding about how the surface of the planet and the inside of the planet itself evolved, we learn a lot about the history of the moon and the history of the Earth-Moon system. So what this is a beautiful video that Goddard Space Flight Center put together, showing the evolution of the basins on the moon. So by collecting samples returned by the Apollo astronauts and age dating them, we were able to understand much more about our system, because again, plate tectonics, which I just mentioned, on the Earth recycles the material on our surface. So we don't have 4.5 billion year old material on the surface of the Earth, except for maybe some meteorites that have fallen. We have native Earth samples of that age. But the moon, the majority of it is around that age. So we were able to bring back these samples and use radiometric dating to understand when they formed. And what you saw at the beginning and kind of the area here that's now flooded by magma is what we see as the dark face of the moon, the Maria. That formed during a period of intense bombardment. So by learning about the moon, we know that about 3.9 billion years ago, the Earth was probably, was definitely exposed to this intense bombardment that we see reflected on the lunar surface. And then finally, this later, more recent bombardment era, we've got these smaller craters, and we can understand the flux of meteorites and larger bodies in the Earth-Moon system that we, again, don't have as well preserved records of, because many of the things that either arrive at our atmosphere are burnt up, or there are many of the impacts that have occurred over the last millions of years on Earth have impacted in water, and we don't have the same kind of record of them. All right, let's go ahead to the next slide here. So, by going back to the moon, as a planetary scientist, there's all kinds of cool stuff to do. There's understanding more about the bombardment history of the solar system. The moon also, because we have those age-dated samples and the cratering record on the moon, we're able to extrapolate that to understand the age of other surfaces in the solar system. We also understand much more about minerals, the distribution of minerals on the lunar surface and in planetary interiors. But by returning to the moon and having a sustained presence and being able to continue to collect samples from different areas of the moon, we could expand that in much more detail. Surface processes on the moon are incredibly important because it's bombarded by the solar wind and these micrometeorites throughout time. So understanding more about those is of great scientific interest. And then finally, something that I didn't get into, but we've now learned over the last decade that there are probably substantial amounts of volatiles on the lunar surface. So there's a record in the deep, dark craters at the poles of the moon. We have a record of volatiles from our solar system neighborhood that may be billions of years old. So it's like a treasure trove of materials, sort of like we find when we do ice cores in Antarctica, but going back billions of years instead of millions of years. And then finally, there's all kinds of things you can do with astronomy from the lunar far side. All right, so that's it for the science geek part of this story. Let's move into talking a little bit more about the human exploration side of this. So of course, living on the moon is the best place to be able to test living off world, okay? It's, there is the idea of potentially going to an asteroid. Of course, people would like to go to Mars, but we don't know what a human body can tolerate. We don't know what the health effects are. And being on the moon, where we're only a short trip back to home, is the safest place to go and understand how to live off the land on another body. So what is APL's role in this? We know the Artemis mission or the Artemis program aims to go back and create a sustained presence on the lunar surface. But in addition to just the human exploration side of that, what NASA really wants to do is to build up this infrastructure probably at the South Pole of the moon, that will enable this ongoing presence on the surface. So this is being conducted primarily through the Space Technology Mission Directorate at NASA, and APL has been brought on as a partner to assist in this. And we were recently given a task order for $30 million over 3 years to really help understand what plans NASA has, what the community has in place, and how we can leverage all of this to make a sustained presence on the lunar surface a reality. So there are 6 areas, technical areas, that we are integrating with the Lunar Surface Innovation Initiative. These involve things like living off the land with in situ resource utilization, accessing some of these dark areas, establishing surface power and infrastructure, and then dealing with some of these extreme environments. What APL is doing explicitly in this is that we have assigned leads to each of these areas, and we're working as a trusted agent. So essentially what we are doing is we are interfacing with NASA counterparts to understand what their plans are, to understand what they think the needs are, and then evaluating those independently with our knowledge of what's going on in the community and of lunar science, to help kind of course correct early on and make sure that they are not too thinking within their NASA box, basically, so that we can help bring in others from members throughout the community. So explicitly how we are doing that beyond the trusted agent role is we're leading something called the Lunar Surface Innovation Consortium. And the goal of this is to bring together members of government, nonprofit agencies, industry, and academia to work together on this return to the moon. So NASA really wants this to be a national effort. and to really engage with technologists throughout the entire United States. And so I'm the director of the Lunar Surface Innovation Consortium, and what we have been really working on is trying to reach some of the communities that have not historically been involved in space exploration, and some of the industries that haven't been involved. So we have over 1,200 participants now throughout the United States, and we do have some international members as well, who meet monthly in each of these different focus areas to discuss technologies. And then we meet as a consortium to kind of do some brainstorming and road mapping and whatnot about some of the highest priority issues. And then the leads for the different focus areas are able to take that information, synthesize it, and with the understanding that they have of NASA's plans, kind of report back to NASA about their ideal direction. So I know I'm getting quite close to the end of my time here. But beyond this, we do have lots of other lunar activities going on. So if you're kind of interested in the consortium, but would like to hear more about some of the orbital and landed activities, we have a number of missions that are kind of centered around mapping, orbital mapping of lunar water, including Lunar Trailblazer, Lunar Flashlight, and then kind of ongoing efforts of Mini-RF on Lunar Reconnaissance Orbiter. And we do have also a newly selected mission, which is Lunar Vertex, which is going to be landing and exploring with a little rover one of the magnetic anomalies on the lunar surface. So if you're interested in any of those, feel free to look me up. So I hope that you found this somewhat interesting. I do want to stress that the moon is not just a step on the way to Mars. It is a compelling scientific target and a very important proving ground for living off-world, and it is very, very interesting in its own right. So I believe I'm going to need to hand off for questions, but I appreciate your time. And if you would like to learn more and participate in the Lunar Surface Innovation Consortium, the website is up here. You can check it out. And like I said, you're also, I welcome any emails to talk about this. All right.